Go.
Thank you, Yannick. So, hi everyone. My name is Hugo. I'm a software engineer at MakerBot. I joined MakerBot in October last year, so it's really recent, and so far it's been a blast. I studied mechanical engineering in school, and this is where I learned about 3D printing and CNC machining, but at the time, these machines were very expensive, and we couldn't get our hands on them. Then I started a software career, and I slowly drifted away. And after about 10 years, I was making too many spacecraft simulators and not enough robots, so I decided to reboot my career. So it was about 6 years ago. I bought myself a Shoreline mill, which was a CNC 3-axis milling machine. So a milling machine is a machine that basically carves in 3D with a Dremel-like tool. The Shoreline mill I had is actually a modification of their manual mill, which has 3 stepper motors and a computer attached to it. Now, such capabilities at that price point, to me, was a signal of an impending revolution. So, the machine also came with a free open source software called EMC2. The job of EMC2 is to take G-code, drive the motors, and make a 3D thing for you. It comes with interesting Python scripts that you can load in the GUI, and as long as they produce valid G-code, just run the machines for you. So this prompted me to learn Python, and I got to learn G-code, unfortunately. So let me take you through this 5-line of G-code program to show you a bit what it is and how arcane it is. So the first line, G21, sets the machines to metric system. Oh, by the way, whatever is not a number in a letter are comments. The second line means a rapid movement to coordinates 3, 5, and 0. 0 is usually the top surface of your workpiece. The G1 command is a linear cut, and you have to give it a speed, and in this example, it will advance 60 millimeters in about 6 seconds. You have other commands like G2 and G3 to do circular arcs, and commands to control your spindle, put cutting fluid, tool changes, and different other things. However, G-code is very difficult to share. You can't really find it on the net because a G-code file will probably contain things that are specific to the machine that it was used with originally, the type of material you want to cut through, and a lot of these things makes it very difficult. Also, 3D modeling tools don't export G-code for the same reasons. There are tools called CAM, which are usually very expensive addition or plugins to very expensive CAD packages, and it's not worth spending $16,000 to run a $3,000 mill. So you're faced with creating your tools or write your own G-code. So I started playing around with Python. I created a few plugins for Inkscape to do engraving and did a few experiments with Blender. That was before the nice BPY interface, so got a little confused. Then I started realizing that I was writing way too much code and I wasn't machining a lot. So I went back to the roots and decided to start a series of little machining projects during which I would use Python to just generate the relevant G-code for me. As time went on, I was accumulating interesting Python snippets and I was putting them into a library I called Hugomatic. So in this example, you see that one line of code creates about 20 lines of G-code to create a round rectangle. I added different things, little scripts to do gear machining, lathe turning, machine tool changes, and then I started to try to see if I could take these primitives and compose them into a bigger parametric projects. I added a GUI and created simple programs to make machining shareable. So I knew that a lot of the users would probably not be very fluent in Python or programming language in general, so I tried to stick to the basics. First, declare global variables, then have a section in which you publish the important variables that to create your forms, read the console line arguments, or display a web form. And then once the parameters are loaded, these global variables would be updated, and then you could start using the different pockets and tools to create your own things. I did a live demo at Montreal Python. It was a big hit, and I got a lot of support and encouragement from my community. So I was able to make easily with Python, with just switching the imports, make a web front end without having to change any code of my scripts. And then I got a bit crazy and I started to do code visualization and syntax highlighting, and then it became a JavaScript project. And again, I wasn't machining enough, I was programming too much. So in the meantime, a lot of things happened. The revolution actually started with 3D printing. So in 2010, I went to the Open Hardware Summit because I wanted to make kits for milling machine operators. I met with Brie Pettis at the breakfast, and he told me about 3D printing. So on the way back to Montreal, I decided to get my hands on a Thingomatic, and I got hooked instantly. I even started to buy 3D printers for my professional work. In 2011, I went back to the Open Hardware Summit, met Brie again, and he introduced me to Adam, the CTO of MakerBot, and that's how I started to work with MakerBot. So I wasn't doing any machining anymore, and then I got this interesting message from a guy named Edward Ford. It says, "Oh, I'm the creator of the Shape Oko. It's a $300 mill, and I like your programs." So, of course, I bought a Shape Oko, and the new Shape Oko is all metal-based, and it's very nice. I'm still in the process of assembling it, so I didn't bring it with me today, but it uses Thingomatic electronics, so it's powered by an Arduino Mega, and it's got 3-stepper controller on board. So, the 3D printing revolution. This is the latest 3D printer from MakerBot. It's called the Replicator, and they're selling like hotcakes. They're a lot of fun, and I will be showing them at the open spaces later today. 3D printing is a different kind of CNC. It's additive rather than being subtractive. So 3D printing is to milling what pottery is to sculpting. The workflow is simple. You go directly from your 3D model to your physical thing. You can make very complex shape that you could not even dream of, even with a 5-axis milling machine like this 3D knot and various things. What I think is really exciting is also the possibility to actually create fully assembled mechanisms and just print them. Now also, because you're always starting with plastic, you don't have to have tools or blocks of different shapes and size. It's very easy to share. Here's an example. My friend David built this thing, published it on Thingiverse. A couple of people liked it. Few people made derivatives, and it's a lot of fun. So let's try to walk through the toolpath generation for 3D printing with some Python examples. Well, it works as follows. First, you need a 3D model, usually an STL file. I personally like to use OpenSCAD, which is like a text-based modeling tool, similar to my code generators, where you just assemble cubes and forms into parametric shapes. Also, you need to decide how thick you want your slices to be in your model, and if you want to create hollow and light objects or dense and solid ones. You can also specify how thick you want the walls to be, and once you get those 3 decisions, you're all set and you can get your own G-code. So, STL files. So, the bunny on the right is entirely made from the triangles on the left. The STL file is super simple. It's 3 points and a normal. If it works for the bunny, it works for an hexagon, and it works for the 3D knot. So it's also very easy in Python to write simple programs to parse these things. On the upper left corner, you see that it's simple to just open a file and yield all the words from it. Then you can compose that into a larger generator that will just read those tokens and create triangles for you. The program on the right opens the Bunny files, reads all the triangle, and it can read about 70,000 triangles in a second, which is very good performance. So, throwing triangles into a text file is not enough to get a 3D printable object. You need to have creatable models with walls with a certain thickness. You can't have holes in your mesh, and all the normals to your triangles must point outside. What does a slice look like? This is actually, the image here shows a slice of the little 3D knot example here. And what you see are the shells, which are the contours of all the elements, which are made of successively insetting the outline polygons. The red grids are the infills, and they're usually a repeating pattern of a specified density. Sometimes you need a bit more. There are also some detachable structures, like the raft that you see on the right, which is kind of this mat on which you can create your objects, and makes it easier to grow from the first few slices. And then there's also support, because when you're printing something like the cat on the left, sometimes you're starting slices in midair. So, let's get into cutting the triangles to get our outlines. Triangles are easy to cut along Z. You can only get 4 types of results. Nothing if you're trying to cut above or under them. 1 point if you're just catching a vertex. 2 points when you're cutting along 2 edges of the triangle. And if you get 3 points, that means your triangle is fully in your plane of cut and it's not contributing to your outline, so you can safely ignore it. So once you know your edges that need to be cut, it's easy also to see where they intersect with the plane of cut. By using a parametric equation of your line, you see here that if so if you want to know if your plane defined by point V0 and a normal n intersects your line between point P0 and P1, you can easily get the equation for the parameter S. And in the case of cutting along the Z plane, it boils down to 4 lines of Python in the lower right corner. Also, segments are important, but they're also oriented, because what you want is all your outlines to be running in a clockwise circle, and all the holes in your models to be counterclockwise, like in this example here of the hexagon. So this is where you use the normal of your triangle, and you just do a cross product with the Z direction to get your direction. And if you cross product again your cutting direction with Z, you get the inset direction, which tells you when you're trying to build your inset in which direction the inside is. So let's put all this together. What you see here, the program this time is on the left side, and it uses the facet generator that we saw earlier to read the hexagon file, and it's looking for all the triangles that intersect at Z equal 1. I'm using a special trick here that splits a triangle into 2 triangles. So if you look at the picture on the right, you can see that this black triangle is actually made of these 2 upper part and lower part. And that's kind of an optimization, because you're going to be cutting your triangle many times, and you don't want to be doing all this management every time. Once you get the edges that cut your triangle, you just use the intersection equation we saw earlier, and then you can write that in a text file. I'm using OpenSCAD in this way, and the result is this. So now this is not much, but already you have, from any 3D object, you can have the whole contour and inside, and if you just send that as G-code to an extruder, you're able to build 3D models. So it doesn't require that much mathematics yet. Once you have your outline, you're interested in knowing, well, what's inside and what's outside, because you want to be doing the infill. So one of the trick here is to cast a ray across your object and watch for all the places where it intersects with your outline. You sort them in order, and then knowing that you start at point 0, which is outside, you know that between 1 and 2 is inside the object, between 2 and 3 is outside the object, between 3 and 4 is inside the object, and so on. So you're going to be doing a lot of these segment-to-segment intersection. And this is how segment intersection works in Python. And it's actually very close to the C code, and that's why you see these semicolons, because I'm actually using both versions simultaneously. So same deal here, you have 2 lines that are parametric, and now you're trying to find the point P that intersects, and once you calculate the S and T for these 2 lines, you know that your intersection is within your 2 segments if T and S are both between 0 and 1. So you repeat for each slice, and you get your 3D model. So I'm going to pause here to say a little bit about parallelism. The problem of slicing an object and making a 3D object out of it is very parallel. I mean, each slice can almost be completely calculated independently. And of course, when you're insetting polygons, this is kind of a linear process. However, because of the amount of slices and everything, you want to be taking advantages of the modern computer that you have. So, how do you deal with parallelism in Python? There are Python threads, but they don't really have a good reputation. You can use multiprocessing, which spawns a lot of processes and uses message passing, or you can use this massively parallel tricks of OpenCL and run it on the GPU. So, how does it work? How can you do the same kind of computation on the GPU? Well, this program here is actually the same segment-to-segment intersection, except it's written in OpenCL, which is very close to C. There are only 2 lines different than the previous Python version I showed you. The the kernel method below takes in a large buffer of these points to intersect, finds out which of the thousands of threads there's available on the GPU, and just calls your method for that one. Now, calling this is a bit more involved than just calling it on the Python. In the upper right corner, this is what you'd have to do given those sets of lines in Python. You just loop around, call your intersection, and get the results. Now, on the left side, it's the OpenCL version. So you need to grab a platform. Then inside your platform, you may have up to several devices, which could be either GPUs or even CPUs. And once you grab the devices you want, you need to send them all the memory information, trigger the execution, compile your program, and then get all the results back to your CPU. It takes a bunch of lines, a few lines more to do it, but once you run it, and this example was run on a laptop, I was able to get easily 100 speed increase in the time to do those calculations. And 2 orders of magnitude is a lot. I mean, it's the difference between waiting 1 second or 2 minutes. And sometimes when you're slicing objects, especially with the new printers, which have multiple colors and very low layer heights, you could be slicing for hours. So that's probably one of the reasons why currently we're kind of focusing on C++ at the moment for the lower level stuff. And, well, sometimes things go wrong. But if you rotate all your slices, you can already build nice objects. This is one of the first objects I was able to build with these algorithms. And finally, the third problem is the one of insetting the polygons. So when you want to make your object with thicker shell walls, you want to go around multiple times. So many things can happen. Usually, well, during insetting, you're still using the edges of your initial polygons and you're just going inwards. Some of the edges disappear when we call those edge collapse events, and sometimes the polygon can split into multiple polygons. And there are different ways to solve that problem. It's a computational geometry known problem, and there are also interesting ways to solve it, maybe using simulations and pathfinding algorithms. I found, during researching for this talk, I found an interesting PySkeleton implementation that has a nice little UI. Sometimes you get it wrong, and your models may look like this. But once you get things going, it's very easy to just translate everything back to G-code, set the temperatures for your heaters, position your extruders on the machine, you go through all the polygons, you start your extruder, you emit a bunch of G1, and then it's down to the firmware that interprets all the little ticks, that interprets all the movements into little ticks, send them to the physical world, into the machine, and you get your object. So I sincerely believe that, yes, we are experiencing a revolution, and the availability of CNC machines for ordinary people is going to enable us to work in different and more interesting ways. So I hope you guys will join the fun and start making things, because really what we're doing is just turning objects into software. So I'd like to thank you and thank the MakerBot team for letting me talk to you about this. Ted, Ben, Far, Allison, Adam, our CTO, and Bree, our CEO. And you can find some code in my GitHub. Thank you.
Hi, that was a very interesting talk. It's great to see Python being used in areas that 10 years ago we probably wouldn't have imagined them there. I just wondered, are you actually working in Python 2 or in Python 3? And if you're working in Python 2, have you made any estimate of what it's going to take to move to Python 3?
Okay, well, actually I'm working mostly in C++ right now because of these problem with parallelism. However, all the scripts that I showed during this talk are all Python 3, except the PyOpenCL one, which I couldn't get to work in time.
Okay, that's very encouraging. Thanks a lot.
Maybe I can just speak loud enough. Why G-code?
So if you have a question, have we got this on?
If you've got a question, please go up to a mic, because we're recording these too.
Okay, perfect. If you control the software and the hardware, you're doing everything, why go to G-code if it's so old and doesn't seem to be working well for you?
Well, G-code is mostly for historical reasons. Actually, in this model and also the next ones, we're using a lot of our proprietary, not a proprietary, but we're using a lot of JSON to send the commands to the machine. So it's mostly for a historical reason, I guess.
Hi. I was wondering if you have to load up the triangles and presumably determine if you have like a manifold mesh. What data structures are you using for that?
Okay, well, the slicing parts assumes that you already have a good model. So we also have checking programs, but those would be run previously. If you're dealing with these kind of problems, there is a good tool that's called NetFab that's proprietary, but it really helps you fix models, especially when things like your modeler generates bad formats. We have a tool at MakerBot that checks for manifold things, but sorry, I forgot its name.
Thanks.
Hi. Hi. I saw at the beginning of the slides you said this machine was additive rather than subtractive. So what does that mean? What's the process of that machine? Is it pushing some melted thing, and how does it work?
Oh, sure. Well, the feedstock is just a filament of plastic that's in a spool behind the machine, right here. And this gets fed into the extruder head, right here. And there's a motor here that pushes it through a very small hole, which is heated to 220 degrees. And this is how the molten plastic is extruded. Now, the bed is also heated to about 100 degrees to make sure the first layers stick well to the platform.
Thank you.
Thank you.
So if we don't have any more questions, I'll remind you that Hugo has got an open space where you'll be running this, right?
Yes, I think it's right now, actually.
Yes. And the open space for you to ask further questions and see this in action is at 12 o'clock, I think. So it'll be very shortly after the talk here. One more question.
Are you familiar with the RepRap and Prusa projects? It's the MakerBot to build other.
Yes, of course. I mean, MakerBot as a company is part of the RepRap project. I mean, it all started with RepRap a few years ago, and even to this day, this machine holds most of its internal structure and to the RepRap project. Also, the current slicing engine that is shipped with MakerBot is called SkyEnforge, and that's also written in Python, and it is part of the RepRap project.
Okay, and then the other question I have, and I know this is kind of not really constructive from a marketing standpoint, but does MakerBot have any plans to implement the same sort of mentality that's behind RepRap, where the ultimate goal is to have a printing robot that can print all of the parts to make another printing robot? Is there any sort of moves in that direction at all?
I don't know. I mean, they don't really ask me those kind of questions. I think I think the idea of a self-replicating robot is interesting, but the business of MakerBot is to make open hardware that make things well. And I think part of the success of the initial MakerBot was that the first laser-cut 3D printers were more easy to procure and probably a bit sturdier than the printed one. I think it's important to have a lot of open hardware companies because I think companies like that are somewhat iconoclasts, and they're changing the way we're doing things. They're not competitive in the same sense, and that's it.
Thank you.
Hi.
Hi.
I was wondering, I read, I don't know if you covered this at the beginning of the talk, I was getting coffee, but there was a woman who had a 3D printed jaw inserted. Are you aware of that? Would MakerBot talk to those people at all, or do you have any thoughts on medical implants and?
Well, we didn't have anything to do with this. The story was picked up in our company, and we talked a lot about it. I myself, before joining MakerBot, I was printing dental parts directly in titanium. Because 3D printing, this is just one implementation of it, which is called FDM, which means fused deposition modeling, where we're melting plastic. But there are other types of machines, some of which make metal parts directly from powder with lasers. And I think it is one of the areas, I mean, bones and things are things that are not available to mass production, so 3D printing is definitely going to make a lot of inroad in there. Thank you.
So Hugo, before I thank you, I'm going to ask you a question. Is there anything for 3D input to help you with modeling? For example, the rabbit. What do you do for scanning and getting things going?
Well, during my stay at MakerBot, I've seen a few 3D scanners around, but the one that gets us the most exciting is the Kinect, because it's cheap, it gets very good images, and of course 3D scanning is kind of the other half of the problem of 3D printing. 3D scanners are very expensive and they're still hard to find. The Kinect is really revolutionary and a lot of thinkers love them. I'm not sure that MakerBot is going to make a 3D scanner anytime soon, but we're certainly going to help others make some.
Great. So, Hugo Boyer, thank you very much. And
thank you.